Hi guys, welcome back. I want to do a few examples involving the ideas from chapters 4 and 5 primarily. I want to go over what those ideas are. So, chapter 4 is about contact interactions, and chapter 5 is about um, getting forces from motion. So, let's look at contact interactions. First of all, the primary source of forces from contact interactions can be uh, understood in terms of an atomic model of solids with interatomic springs. The normal force can be thought of as a sort of a mattress force. When you lie down on a mattress, it compresses the springs. When you set something on a solid object, it compresses the atomic springs. Friction is sort of what you get when you try to slide two surfaces against one another, and the interatomic springs, have to bend and twist in funny ways. And buoyancy, of course, is a contact force between a fluid, which could be a gas or a liquid, and an object immersed in the fluid. And so we'll have a chance to talk a little bit about that in class and maybe do a couple of examples. The idea of force for motion is that if you observe the momentum of an object over time, you can deduce from that the net force. The parallel and perpendicular components of the net force have different effects on the momentum. So the parallel component, the component parallel to the momentum, changes the magnitude of the momentum, while the perpendicular component makes changes to the direction of the momentum. Once known forces are accounted for, and dp dt gives you the net force, the difference between the net force and the sum of all the known forces can be used to compute the magnitude and direction of the total unknown force. So, there's lots of problems we can solve. There's like masses on springs and balls on ropes and complicated systems with more than one spring and more than one mass. You can handle gravitational systems like objects orbiting one another and roller coasters going over hills and stars going around galaxies and planets going around stars, objects moving in funny ways, roller coasters going at the bottom of a hill, and so on. So I'm putting all these pictures up here just to illustrate the variety of the kinds of problems that can be solved with this approach. And it can also be overwhelming if you think of these as all very different things and all the different possible things that can happen. But what I want to emphasize is that all these problems can be solved using a relatively simple strategy. First, you identify the forces that are acting. Then you write out the momentum principle for each object in the system, and then you solve the resulting equations. So let's do a couple of examples and see how that works. Example 1 is you've got a couple of blocks, mass 1 and mass 2, being pulled by a rope or something, and the question is, what's the maximum force with which you can pull the bottom block without risking the top block slipping off? And just for simplicity, I'm assuming that the interface between the bottom block and the ground is frictionless. So it could be like an oil-covered, very smooth floor or an air hockey table or something. Before you try to do this example yourself, I'd like you to watch the video on free body diagrams because it gives a lot of hints about how you solve these kinds of problems. And before you watch the following segment in which I go through and detail the solution step by step, I want you to stop now and try to identify yourself the forces acting on mass 1 and the forces acting on mass 2. Go ahead and pause the video now and get out a sheet of paper and draw the picture. See if you can do it. Okay, let's take a look at mass 1 and mass 2. I'm going to start with a diagram of both of them. So mass 1 is sitting on the ground. Mass 2 is sitting on top of mass 1. And there's some kind of external force here, say from a rope or something. So I'll call this the force of the rope acting on mass 1. Now what I want to do is to draw a free body diagram for mass 1 and a free body diagram for mass 2. And the way I do that is to draw the object I'm interested in solid lines, and then everything else I make kind of a dashed line around it. So let's see how that works. So I draw mass 1 as a solid block. And then mass 2, I'm going to draw kind of as a dotted line. So let's make a kind of a dotted line there. It's kind of hard to draw with this software as a dotted line. But anyway, we'll do our best in it. Draw the ground as kind of a dotted line. Okay. Now let's identify the forces acting on mass 1. Obviously there's the force of the rope. So that's the force of the rope acting on mass 1. Now the weight of mass 1 is going to act down, so we can call that W. And that's the Earth acting on mass 1. Call it W1, say. Then we're going to have the normal force. Let's call that N1, which will be the normal force of the floor acting on mass 1. There'll also be a force for mass 2 acting on mass 1. Let's call that N21. That's the force 2 acting on mass 1. And what else have we got here? Now, there's no friction between the floor and mass 1, so I don't have to worry about that. But there is going to be friction between mass 1 and mass 2. And by reciprocity, that means there's going to be friction between mass 2 and mass 1. So I'm going to have to put that in at some point. But let me leave that out for now. Let's focus on the free body diagram of mass 2. So here we have mass 2. And what's it going to have? It's going to have a dotted mass 1 underneath it. So I'll kind of dot that in here. And then what forces are acting on that guy? Well, it's got W2, the weight of mass 2, which is, of course, the Earth acting on mass 2. It's going to have a normal force N12, which is going to be mass 1 acting on mass 2. And let's see, what else have we got? Well, there's going to be friction between mass 1 and mass 2. And which way is it going to go? Well, obviously mass 1 is going to move to the right, and mass 2 wants to go with it. There'll be a frictional force pushing on mass 2 to keep it moving along with mass 1. And obviously, the statement of the problem says we want to find the maximum applied force that will not cause the top block to slip relative to the bottom block. So that means there's got to be a frictional force somehow acting to the right of mass 2 acting on mass 1 acting on mass 2, sorry, like that. And by reciprocity, there must be a reciprocal force, or a Newton's third law reaction force to that guy that acts on mass 1. So I'm going to draw that guy in, and we'll call this F of 2 on 1. And those guys are going to be equal and opposite. So I think that's it. That's all the forces. We have 1, 2, 3, 4, 5 forces acting on mass 1. 1, 2, 3 forces acting on mass 2. We're neglecting any friction between the floor and mass 1 just because we have already 8 forces in the problem and we don't really need a 9th. So in order to make it an interesting and rich problem. So let's move on. Now that we've identified all the forces that are acting, what I'd like to do is to scrunch these pictures up a little bit, scoot them to the corner, and let's start writing down some expressions for the rate of change of momentum. The idea is for each object in our system, we're going to write down the momentum principle, and let's see how that works out. Let's start with the momentum principle applied to block 2. So that would say dp2 dt. It's got to be the rate of change of momentum of block 2 must be the sum of all the forces acting on block 2. So that's going to be the weight acting on block 2. It's going to be the normal force from block 1 acting on block 2. And it's going to be the frictional force, call it F12, of block 1 acting on block 2. Bingo, that's it. Next, we need to do the same thing for block 1. It's a little more complicated because there's more forces, so we say dp1 as a vector dt, that's the rate of change in momentum of block 1, it's going to be the sum of 5 forces. So we're going to have the weight of block 1, it's the earth acting on block 1. Then there's going to be the applied force, F of the rope, right? Then there's going to be the normal force from the floor. Then we've got 2 more forces that are produced by block 2. There's the normal force from block 2, and there's the frictional force from block 2. And that's it. So we've got 5 forces acting on block 1. We've got 3 forces acting on block 2. Now, I'm going to tell you that all the problems from chapters 3 and 4 can basically be analyzed in this fashion. Identify all the forces that are acting, write out the momentum principle for each object in the system, and then identify any, that's it. That's the main physics is right there. Then the idea is you have to sort of go in and apply the reciprocity rules, apply what you know about how friction works, and then break these vector equations down into x and y components, and then what you're left with is a bunch of equations and a bunch of unknowns that you have to solve in order to figure out the answer to the actual physics question you're trying to ask. So let's take these guys one at a time, make those substitutions, make those relationships clear, and then solve the math. So here we go. First, I'm going to scrunch these guys up a little bit more, get them out of my way a little bit so I can work with the component equations, but I don't want to lose them completely because obviously they're important. Let's start with mass 2 again. I want to break this relationship into x and y components so I can think about it more simply. Notice that in the x direction, the only force that counts is the friction force. The forces in the y direction are these guys, the weight and the normal force, and there's nothing actually happening in the y direction. The rate of change of momentum is 0 there, so these guys actually have to cancel. So let's start with the easy stuff. The other thing is, of course, we know the weight of mass 2 is just m2 times g. So in the y direction, I'm going to have, let's talk about mass 2. And we'll have x, and we'll have y, and we'll say dpx dt is going to be f12. That's it. Whereas in the y direction, we'll have dpy dt. Let's put that dpy dt. We'll have the normal force of block 1 pushing up on block 2 minus the weight. And of course, there's nothing happening in the y direction for the y momentum. The y component momentum is going to be constant, so the rate of change of the y component momentum is 0. This is incredibly important to recognize because it means this equation is simple and easy to solve, and it just says that n12 must be equal to m2g. So actually that's also quite nice because you know that by reciprocity n12 is connected to n21. So n21 must also be equal to m2g in magnitude, right? So in magnitude those guys are the same. Nice. Okay, let's scoot these guys up and work on the other object, mass 1. First, let's look at the x direction. In the x direction for mass 1, we've got dpx dt. And what's acting in the x direction? The weight doesn't act in the x direction. It only acts in the y direction. The rope force acts in the x direction. And the frictional force for mass 2 acts in the x direction. But the normal force of the floor, the normal force of mass 2, and the weight only act in the y direction. So I'm going to leave those guys out. So this is going to be the force from the rope. And then remember, the force from mass 2 on mass 1 points in the negative x direction. So I'll say that's minus F21. In the y direction, I've got dpy dt for mass 1. it's going to be minus the weight. It'll be plus the normal force from the floor, let's call that N1, and it'll be minus the normal force from mass 2-1. Okay, but mass 2-1, remember, that's just m2g. So in fact, I can erase that and put in minus m2g. Now, what's happening in the y direction? Nothing. The rate of change of the y component momentum is 0, so that means this guy must be 0. And that actually tells us that n1 must be equal to m1 plus m2 times g. Nice. The total weight of both blocks is equal to the normal force pushing up. Now, if there had been a frictional coefficient between the floor and block 1, we would use this to calculate the frictional force between the floor and block 1. But happily, there is no such friction in the problem. Excellent. So, let's slide this guy on up now, and let's look at the x component. Now, one thing I want to point out is that the x and y components of, the friction of 1 on 2 and 2 on 1 are connected together. By reciprocity, they're the same force. So that means those guys are equal, and we're going to need that in a minute. So let's look at the rate of change of the x component momentum of block 1. Now, we know that F21 is equal to F12 is equal to the frictional force between the block 1 and block 2, that top surface. But we know how friction works. This is a force of static friction, so it's less than or equal to the coefficient of static friction times the normal force of block 1 on block 2. But we already worked that out. That had to be equal to m2g because the top block is in vertical equilibrium. There's nothing happening vertically. So this is mu sub s m2g. There you go. But that's also equal to the force of the magnitude of the force of block 2 on block 1. So in fact, we know this guy. This guy, F21, is simply mu s m2g. So in the x direction, we get dpx dt is equal to fr minus mu s m2g. But what is dpx dt? It's the mass of block 1 times the rate of change of its velocity, m1 a1 x, right? The x component of the acceleration. The other thing we have to recognize is that the x component of acceleration of block 1 and the x component of acceleration of block 2 have to be the same because they're connected together. They have the same velocity at every moment in time. Therefore, they have the same acceleration at every moment in time. So I'm going to move this guy down and remind you about the rate of change of a momentum of block 1. That's this guy right here. It's just equal to F12. So that means m2, the mass 2 times a, the rate of change of its x component momentum, is equal to the same force that produces the force of friction for block 1. So let's scroll this guy back down, and let's put this in. This is for block 1. Just as a reminder, for block 2, we had dpx dt. This is block 1. This is block 2. It happened to be equal to simply F12, which was mu s m2g as well. But that's also equal to m2 a2x. But notice here, this m2 and this m2 cancel. So that means a2x is simply equal to mu s times g. But that's also equal to a1x, which we can just call a because they're the same number, right? So I can get rid of this a1x nonsense and just write this as m1 mu s g. Beautiful. And now we have our result, because the only thing we don't know in this picture now is the force. So I can solve this top equation for the force, putting in the acceleration, putting in F12, I'll put in all that stuff. So what I have is Fr minus mu s m2g is equal to m1 mu s g. And that says that the biggest Fr can be is mu s g times m1 plus m2. Let's take that back to the original problem and see what that tells us. Okay. Example 2 involves a playground with a merry-go-round, and you sit on the merry-go-round and your friend comes along and starts pushing, and the question is, at what point do you start to slip off the merry-go-round? You've got a definite coefficient of friction, you've got a definite distance from the merry-go-round, and the question is, how long does it take until you start to slide? So again, I'd like you to stop now and draw a free body diagram. Try to identify all the forces that are acting. Okay, this is a problem of a merry-go-round. I want to draw the merry-go-round looking from above and also looking from the side. So from above, the center of the merry-go-round is here. You're sitting here. A distance, let's say this distance is r, okay, your distance from the center. Here's the axis of the merry-go-round. Here you are. And this distance is, of course, the same distance, r. And the idea is to, but the whole point is the merry-go-round is actually spinning. And so you're moving with an ever-increasing speed. You have a friend who comes along and gives you a push. They keep going faster and faster and faster. The question is, at what speed will you start to slide off the merry-go-round? And the key, of course, is to draw a free body diagram of yourself. And so here you are, modeling you as a block, okay? You're a distance r away. What forces are acting on you? Well, there's the weight force from the earth. There's the normal force from the floor of the platform. This is the earth acting on you. This is the platform acting on you. And then there's also going to be a frictional force. You're going to want to slide to the right in this picture, but because of the friction between you and the platform, there's a force preventing that from happening, F platform on you, but it's a frictional force. But that frictional force has a maximum value that it can possibly be, and it's that maximum value that's going to give you the limitation on how fast you can go. So let's scoot these guys over to the right here a little bit, and let's write out the momentum principle just like we've been doing. We've got dp dt of u is the sum of three parts: the normal force, the weight, and the frictional force, F. Right? Now we also have an x and y component as usual, so x and y component, we'll put that in. We've got dpx dt, dpy dt. In the x direction, what do we have? Well, there's only really one guy. It's the frictional force, and it's in the negative direction, minus the frictional force. In the y direction, we have two guys. It's the normal force minus the weight, but of course the weight is your mass times g. Now in the y direction, you're not going up or down. Your momentum in the y direction is constant, so that's 0. So that tells us that the normal force in this case is just equal to mg. Now the frictional force, we don't know what that guy is. It's going to depend on the speed and so on. But we know it has a maximum value. And the maximum value of the frictional force, the maximum value it can possibly have, is mu s times the normal force. But we've already worked out what the normal force is, so we can actually calculate that, mu s times mg. So that's the maximum value the frictional force can take on. Now, what about the only thing we don't know yet? So we know the y component of the rate of change in momentum, but what about the x component? Well, this guy's moving in a circle, and what we're learning in Chapter 5 is that when things move in a curved trajectory, they get a perpendicular component of the rate of change in momentum. So that is dp dt perpendicular, right? Turns out to be v over r times the momentum itself. Now, this obviously is non-relativistic, so the momentum is just mv. So the magnitude of the perpendicular component of the rate of change in momentum is just mv squared over r. So we can simply put that in, but we do have to be concerned with one thing, and that is which way does it point? It turns out it always points toward the center of the circle. And by looking at the diagram, you can see that that is the same direction as the frictional force. So the frictional force is actually the force that's going to be responsible for producing this rate of change of momentum. So once again, I want to scrunch these things up a little bit and get them out of my way. But I want to finish off this guy by pointing out that dpx dt is going to be minus mv squared over r, since it points in the minus x direction. That's going to be equal to minus the frictional force. So let's write that out. Minus mv squared over r is equal to minus the frictional force. This is the x component of dp dt. And if I solve that equation, you can see that it means that the v at any moment is going to be the square root of the frictional force times the radius of the circle divided by the mass. But the maximum value the frictional force can have is mu s mg, so I can put that in and get that the maximum speed is going to be mu s mg r over m. The m's, of course, are going to cancel, and that leaves me with the simple result mu s mg. Fantastic. The final example is the example we're doing in the classroom of the pig swinging around in a circle. I'm not going to put numbers in right now because you're going to measure the numbers, the length of the string, the diameter of the circle, the time it takes to go around, and all that stuff. What I'd like to work out next is the relationship between the angle and the speed of the pig, the radius of the circle, and the strength of the gravitational field. So let's do that right now. Okay, so you probably recognize this pig diagram from the picture in the slides. I want to point out that in the lab, you guys are going to be measuring the length of the string here, and you're going to be measuring the diameter of the circle. But the math that we used to solve these guys in the from the theory involves the radius. So the radius of the circle is, of course, going to be half the diameter. So pay attention to that. When you measure the diameter, recognize that the radius of the circle is actually going to be half that. The other thing we should note is that if you know the radius of the circle and you know the length, of course, you can work out the angle theta. So it's oftentimes convenient to work with the angle theta more so than it is to work with the radius of the circle and the length of the string. So let's. What I want to focus on in this example is simply the free body diagram of the darn pig. So let's take the pig and let's think about what forces are acting. Of course, it's got weight, which is going to be the force of the earth acting on the pig. And then it's also going to have a tension in the string that connects it to the ceiling. That's the tension of the string acting on the pig. And really, that's it. Now, the other thing you can notice from geometry is that this angle theta and this angle theta happen to be exactly the same angle. So we can simply write the momentum principle as the dp dt is equal to the sum of these two forces, the tension plus the weight. But as we've done in the other cases, it's convenient to break this guy up into x and y components. So let's go ahead and do that. And has also been my habit, I'm going to scrunch this up a little bit because it's too much and make use of the space a little better. So let's write out the x component of dp dt and the y component of dp dt. The x component, of course, just says dpx dt is equal to the x component of the tension, which I think you can see is the tension force times the sine of theta. And there's nothing else. The weight force has no x component, so that's the only game in town. Let's look at the y component of dp dt. Now there's two forces that have y components. The tension has a y component, t times the cosine of theta. And of course the weight has a y component, which is downward, which is minus mg. Now in the y direction, there's nothing happening. The pig is not going up or down. It's not changing its y component of momentum. So I can replace this guy with 0. In other words, these guys add up to 0. But in the x direction, the pig's moving in a circle. In the picture on the left, you can see that at that moment, which is where I have the free body diagram, at that moment, the direction toward the center of the circle is to the right. So just like we did with the merry-go-round, this is going to end up being mv squared over r, but in this case, because of where we've drawn the diagram and the moment in time we chose to draw the free body diagram, that's going to be a positive mv squared over r. So really I end up with two equations. I end up with mv squared over r is equal to t times the sine of theta, and I end up with mg is equal to t times the cosine of theta. And so you can see that if I take the ratio of these two guys, I'm going to get v squared over rg. That's going to be equal to the tangent of theta. So there you have it.